again, class. How are you guys today? You getting tired of being inside? Is your mom giving you lots of extra work to do? Those are some of the things that are happening here in our house. I want to do lesson 12.6 for you today. Chapter 12, as you know, is about circles, and we have looked at different parts of a circle, different segments related to a circle, including radii, diameter, chords, secants, and today we're going to look at tangent segments a little bit. We talked about a line that is tangent to a circle, is perpendicular to the circle at the point of contact at the end of a radius. And today we're going to look at one of the things that results from that. So, Chapter 12, Lesson 6, that's page 516 in your textbook, if you want to follow along with me. The first theorem that we are presented with this week has to do with, or today, is about tangent segments. So let's define what a tangent segment is, first of all. A tangent segment is a segment, a line segment, that is tangent to the circle, and one of its endpoints is on the circle. So if this line PA continued over here, we wouldn't call that a tangent segment, but because A is on the circle, we call this a tangent segment. Our theorem says that the tangent segments to a circle from an external point are equal. So if I choose a point off the circle, say point P, I can draw two segments that are tangent to the circle from that point. I could have chosen P to be up here or down here, super close to the circle, really far away from the circle. Any of those, it doesn't matter. P could be on this side of the circle. But right now I've got P in the same plane as the circle, and it is going to be, and I can draw two tangent segments to the circle from that one point. Those are called, these tangent segments are equal to each other. And we are going to prove why that is true. All right, you can go through, Greta. It's okay. Just be careful not to knock that, please. All right. First of all, I'm going to make some triangles because we know what to do with triangles. We're very comfortable with triangles. So I'm going to draw OA and OB. And what can you tell me about line segments OA and OB? They are radii to the circle, or radii of the circle, and because of that, they are equal to each other. Excellent. Now, I'm trying to draw triangles. I have not successfully drawn a triangle yet. What do you suppose I'm going to draw? Well, I could draw chord AB. That's not going to be super helpful. Or I could draw OP. That is going to be super helpful. Let's see why this is so helpful. All right. What appears that it might be true about those two triangles? You don't know, I understand that, but it is possible that these two triangles are congruent to each other. Let's see if we can prove that. Well, I've got these two line segments are equal since they're radii. I've got OP equal to itself, handy dandy reflexive property. There's one other thing that I know that I haven't marked yet. Do you know what that is? How did I describe PA and PB? I said they were tangent segments. And tangent segments are tangent to the radius at the point of contact. So AO is perpendicular to AP, right there at A. And similarly, OB is perpendicular to BP at the point of contact, right there. Okay, is that enough to prove these triangles congruent? Well, I have two sides and one angle in each of them. Side-side angle is not a postulate or a theorem. However, my angle is a right angle, which means that I've got a right angle, I've got a leg of each of those right triangles and the hypotenuse. So by hypotenuse leg, those two triangles are congruent to each other. Now, if those triangles are congruent to each other, then all their corresponding parts are equal, which means that BP is equal to AP because corresponding parts of congruent triangles are equal, CPCTE. All right, excellent. Any questions? If so, look in your book or shoot me an email. Okay. The second thing that we learn in this lesson is something about chords that intersect inside of a circle. And it is called the intersecting chords theorem. Really creative name there, huh? All right, I'm going to go with a different color. We've got orange this time. All right, so handy dandy circle. I'm not going to draw my center this time just because it's not super helpful or necessary. It'll be just maybe a little distraction if I do that. So I'm going to draw one chord, AB, and since it's called the intersecting chords theorem, I suppose I should draw another chord that intersects this chord, right? So I'm going to draw a chord CD, and I just don't want it to look too much the same. C, D. Okay. And those two chords intersect in this point P. The intersecting chords theorem says this. If two chords of a circle, if two chords intersect in a circle, we've got that part, the product of the lengths of the segments of one chord is equal to the product of the lengths of the segment of the other chord. This is when you go, would you slow down and say that in English for me? So let me try to do that for you. It says that if I look at one chord and I multiply the two parts of it, CP times PD, that equals the product of AP times BP. All right, that's what the intersecting chord theorem says. That I can take those chords, they're already divided into two different parts, and I can multiply those two different parts of one chord, and they should equal the product, or the answer that I get when I multiply the two different parts of the other chord. So I'm not going to multiply CP times CA, no, or PA. Those are parts of different chords. I have to stay on the same chord and multiply those two segments of the one chord, and they should equal the product of the two segments of the other chord. Now let's look at why that is true. And I'm going to go ahead and leave my squiggles here. Hopefully that's not going to be too much of a distraction. And I'm going to draw CA and PD. Okay. Now I have, conveniently enough, a couple of triangles. And seeing as how this is geometry, we do love our triangles, don't we? All right. How is this going to help us? Well, let's see. I'm going to give some names to these angles. I'm going to call that angle 1 and angle 2. And over here I'll have angle 3 and angle 4. Can I prove anything equal to itself at this point? Well, the first thing that I saw that I could prove is that I've got vertical angles, and I know that vertical angles are equal. I'm going to choose those vertical angles that are inside of the triangles, although I could choose the other ones if I wanted to, but I'm going to choose these two angles and say that they're equal to each other. All right, that's nice. But of course, one pair of angles being equal doesn't help me prove that triangles are congruent or even similar. Do these triangles look congruent? They certainly don't look congruent. Do they look like they might be similar? Maybe. So that's what we're going to try to prove. We're going to see if we can prove that these triangles are similar, and if so, then maybe we can get to here. All right. Let's look at angle 1 first of all. Angle 1. Angle 1 is an inscribed angle, and it intercepts what arc? Angle 1 intercepts arc AD. So angle 1 equals half the measure of arc AD. What other angle intercepts arc AD? Arc AD is also intercepted by angle 3. Angle 3 equals half the measure of arc AD also. Therefore, what do you see? Angle 1 equals angle 3. Dun, da, da. Hooray. Angle 1 equals angle 3. Perfect. All right. We've got angle. That's fabulous. Let's just see if we can get that third angle for fun. Angle 2. What does angle 2 intercept? Angle 2 is an inscribed angle, and it intercepts or cuts off this little arc CB. So angle 2 equals half the measure of arc CB. And likewise, angle 4 cuts off arc CB, intercepts arc CB, so angle 4 equals half the measure of arc CB. And therefore, angle 2 equals angle 4. 1, 2, 3, 1, 2, 3. All right, so these triangles are definitely similar to each other. Now let's work to get that similarity in the right order, okay? Let's start with this outside chord. Let's start at A, C, P. Triangle ACP is congruent to what? Well, I'm going to start again with this outside chord, but do I start with B or with D? Since the outside, since I started with A here, and A corresponds to angle 2, we're going to start with D here and go D, B, P. D, B, P. All right, so A, P, or ACP, I wrote is equal, I want to write is similar to triangle D, B, P. Excuse my lack of triangle symbol there. My board is kind of small up here. Okay, now let's look at some corresponding parts. If I take PC, CP, and put it over PA, CP over PA, CP over PA, what does that correspond to in my larger triangle here on the right? Well, CP corresponds to BP. CP corresponds to BP, and PA corresponds to PD. So, I've got a mistake here, PD, sorry, it corresponds to PD. Said it correctly, just didn't write it correctly. Okay. Now I am going to cross multiply like I do when I have a ratio, a proportion like this with an equality of two ratios. So CP times PD equals, I multiply the other side,